Hi, in this video, we will study how to do matrix operations. So remember that we defined two matrices, A and B. So A is the matrix, the 1, 2, 3, 4, 2 by 2 matrix with entries 1, 2, 3, 4. So B is matrix with the entry is 3, 0, 0, 2. So what is A plus B? Just that is done in the same way as operation for scalars. So A plus B is this. So that means the 1, 1 entry of A and the 1, 1 entry of B are added to 4. Okay, 1 plus 3 is 4. And 3 plus 0 is 3. So by definition, the matrix addition and also matrix subtraction are done element-wise. So it's the same as usual operations. So A minus B, 1 minus 3 is negative 2. And here, maybe 2 minus 0 is 2. How about A times B? If you typed A times B in R, then the result is this. So this is actually component-wise. Product. So remember that the A is 1, 2, 3, 4, and the B is 3, 0, 0, 2. So A times B is, okay, so 1 times 3, so that becomes 3, and 2 times 0 becomes 0, and so on. 4 times 2 equals 8. So this is not usual matrix product, but this is element-wise the product. So how to do matrix product? Usual product. That is actually, it's a little bit complicated. A percentage times percentage B. So this is the symbol for matrix multiplication in R. So this is usual matrix product. If I don't say anything, matrix product means this product. So this is 3, 4, 8, 1. So remember that the matrix product is defined by the row vector, the inner product of the row vector of the first one, A, and the column vector of the second one. So first row of A is 1, 2, and the first column of B is 3, 0. So 1 times 3 plus 2 times 0. So that is 3 plus 0, so 3. So that comes here. And the second row of A and the first column of B, the inner product of this, that is the 3 times 3 plus 4 times 0. So that is 9. So 9 is here. And again, 1, 2, and 0, 2. So second column of B and first column of first row of A. So 1 times 0, 2 times plus 2 times 2. So that is 4. So this is the usual, the matrix product. Okay, so division. So we don't have matrix division, but the inverse matrix. Inverse matrix is obtained by the solve function. Solve function of A is inverse of A. So inverse of A. So this is negative 2, 1, 1.5, negative 0.5. So that means solve of A, matrix product A. So this becomes identity matrix. That is 1, 0, 0, 1. So actually, there's some rounding error. So actually, this is almost 0. So 4.4 times 10 to the power negative 16. So basically, this is 0. And 0, and this is 1 times 10 to the power 0. So 1, exactly 1. So 1, 0, 0, 1. So unit matrix we can get. And remember that the other way around, matrix product of A and the solve of A, this is 1, 0, 0, 1 again. So in general, the matrix multiplication is not commutative. So AB and BA are different. But A times A inverse of A times A inverse and A inverse times A are the same in matrix product. Yep. So next we think about the matrix times vector. So like AX. So matrix A is this. So we define the vector X. So vector is defined by this the grammar C parenthesis. So suppose X is 1, 2 vector. Then what is the A times X? Again, we use the matrix product. So in this way, the X is recognized as a column vector, or I would say 2 by 1 matrix. So this is 5, 11. So you can see the one inner product of first row of A and X. That is 1 times 1 plus 2 times 2. So that is 5. And 3 times 1 plus 4 times 2 is 3 plus 8, so 11. So 5, 11. So you can get this. But if you type XA, still this works. So in this case, the X is recognized as row vector. So just R recognize this vector so that the matrix product is defined. Okay. So if we regard X as a row vector, we can calculate matrix product. Then this is 7, 10. So you can see X is 1, 2. So row vector, 1, 2 as row vector. So we think about inner product of this and first column of A. So 1 plus 1, 1 times 1 plus 3 times 2. So that is 7. And the other one is 10. So this is how we do matrix calculations: addition, subtraction, multiplication, and inverse matrix. And also that we think about the matrix times vector. And the next, diagonal matrices, diag of 2. So this gives the 2 by 2 identity matrix. So 1, 0, 0, 1. So diagonal 3, the diagonal matrix, the identity matrix 3 by 3. And how about the what happens when we put vector in the input of this diag function? Then this makes diagonal matrix with entries 2 and 4. So this is somewhat contradictive to the original one. So if you put scalar, you get the identity matrix with specified size. So if we put 2 by 2 matrix. But if you put vector, these 2 and these 4 are regarded as just the diagonal elements. So 2, 4. And also transposed A. So just we interchange the column and row. So basically that we make we mirror the all elements with respect to this diagonal line. So 3 comes here and the 2 comes here. Transposed A is the T of A. So T parenthesis A. So these are basics. And next we think about the determinant. So determinant of A. What is the determinant of A? So determinant of A. So this is basically the area of the parallelogram, the spanned by these 2 column vectors, so 1, 2, and 3, 4. So that is defined by, that is calculated by the 1 times 4 minus 2 times 3, but that is done by determinant of A. So dt of A, then you can get the determinant. So next, the eigenvalues, eigenvectors. So eigenvectors are important vectors for matrix. So eigenvectors becomes just scalar times itself after you multiply the matrix from the left-hand side. So that is obtained by eigen of A. So eigen of A becomes this. So you can see that these column vectors, negative 0.4 and negative 0.90, this column vector, and negative 0.82 and 0.56. So these two column vectors are eigenvectors, and corresponding eigenvalues are this 5.37 for the first column, negative 0.37 for the second one. Okay, so just we double check if this column vector is really the eigenvector. So we subtract, we extract this first column. So E $ vectors and first column. Okay, so this is the first column, and we multiply the matrix A from left-hand side. So this way. Then this becomes negative 2.23. But actually, negative 2.23 is 5.37 times larger than negative 0.41. So this entry after multiplying A, so the first entry of this vector becomes 5.37 times larger, and this should happen for the second element also. So negative 4.88 divided by this one is also 5.37. Okay, so remember that the A times eigenvector, I would say the eigenvector of eigenvector, I would say maybe E1 becomes 5.37 times E1. So this is the property of eigenvectors. So you can check the other one. So the other column vector, if you multiply A with this vector, then the result is negative 0.37 times this vector itself. Okay, so these are operations in matrices. And at last, we would like to discuss how to name row and column of matrices. So suppose the matrix A is just the 3 row, 3 columns, so 3 by 3 matrix. And we want to name these rows and name these columns. For example, suppose that these are data for 3 people. The first row is the first person, and second person. And these 3 columns are height, weight, and body mass index for these 3 people. Then how to name these column and rows. So, and the row names function. So this can define the row names of A. So for example, the first person, Alex, and the second person, Bob, and the third person, Chris. And also the column names. The column names is defined by the call names function. And you can, for example, put height and weight and BMI. Then A becomes this. So this is convenient when you want to see what it means. And also you can extract these names from this matrix. For example, row names of A returns this. So if you want to pick up this name, row names A, bracket 2, then you can extract this as Bob. So these are basic operations and how to name rows and columns for matrices.